So welcome everyone to lecture 3 of our winter school on ethology. Okay, so lecture 3. So where did we leave off yesterday? So we coded the cousin model. We went through steps to understand how you think of an agent-based model and how you put down all the interactions, the framework, and everything in place, and then it ultimately results in uh, something like this. We saw this video earlier, and we did the simulations also that led to behavior of this sort. And what I would like to point out here, that this is what is called a forward problem in engineering literature. Typically, it's an engineering thing to say that this is a forward problem. What do I mean by that? So let's say I know the interactions rules, which is what I knew when I started off writing the cousin model. I knew the properties of the agents, the state of the agent, this and that. And we could even program, here all the agents are identical, but you could even have non-identical agents and so on. Then we knew the information of the domain, the arena, and what the interaction was and so on with the arena. And once when you know all of this, all what you're doing is doing a simulation which produces the behavior that you see, which is of the collective. So now, where are these rules coming from? They are motivated by observations. There are some intuitions, the domain-specific understanding that you have, which you use to write these rules down. Many times it could also be phenomenological in nature. What I mean by that is you have data, you made a lot of observations, and from there you hypothesize how interactions are, and then you plug that, some version of that, into these simulations, and you are essentially simulating the emergent behavior that emerges from the rules that you've given. So this is what is called a forward problem. You supply everything that is required, all hypotheses, all the models, all the details, everything about the agents, and then you get this collective behavior at the level of the group that emerges out of this. Similarly, one can now think of an inverse problem. So what would that be? So we've been seeing this video again and again, right? So you have a real experiment where there are real fish doing something, and you are interested in explaining what's. Problem is one where you ask the question, what is the collective behavior observed in this experiment? See, that's a very specific thing to ask, right? So what is a collective behavior inspired from an experiment is different from asking what is exactly happening here. Can we infer that from data? So in some sense, you use data even in the forward simulation to get these rules. You didn't start off in vacuum. In some sense, you're asking this thing, can we rigorously derive some useful information from data that you can extract from an experiment of this sort? So okay, just to recap quickly what I said in the last two slides is that what we solved yesterday is a forward problem. You supply the simulation with every detail that is required, and then you solve it in a forward manner. You go from the details to the emergent behavior. But most often, we are interested in understanding a system, in which case you're actually interested in solving the inverse problem here, which is in some sense asking the question, what is the collective behavior observed in this experiment? For example, the video that you're seeing. Can we take data from here and rigorously use that to derive some useful information? So that's the question where we start when we talk about inverse problems. All right. And what could that mean? It could mean that we are asking the question, what are the interactions that are actually happening? How are the fish in this interacting with each other? That's a question we can ask. What are the strength of these interactions? What are the rates at which these interactions are happening, and so on? So all of this are part of the inverse problem. You could ask, what is the topology of the interaction network? So there was metric and topological that we discussed yesterday. So exactly what is happening here? How are these fish communicating? How many fish are they communicating with, and so on? And another question you could possibly ask is, in general, what is the dynamics of this collective? Someone yesterday pointed out, instead of doing a variety of simulations to determine the global behavior, is there a much more elegant way of doing it? So is there a group level equation that you can derive, which is going to shed light on what kind of dynamics you're likely to observe? So things of this are, can we rigorously throw light on any of these kind of questions, is what is under the broad umbrella of inverse problems in collective behavior. All right. So When you're talking about this, we ask the question, so what in this observed collective motion should we care about? All right, we qualitatively described a lot when we gave you the forms. We did that again yesterday. But if you were to quantify, what would you do? So one of the clearly identifiable things is the fact that there is some kind of a consensus direction. So they are able to come to some consensus with respect to where they are going. And clearly they are staying together, right? So what would be some order parameters that characterize these kind of behaviors? Okay, that's a question. Um, so let's begin. Let me give you an example. So going in a common direction is what is commonly termed as polarization in this literature, because they're polarized, they are all chosen one direction and so on. This is an example order parameter for polarization. Let's just try to understand this. You see the 1 by n, so obviously it's an average. Okay. Now, what is it averaging? There is some ek that I've written, right? Typically, I'm using some notation to note that e is also bolded, which means I'm referring to it as a vector. Okay. So in 2D, when you look at this fish, they are going in some direction at every instant of time, right? So there is a direction associated with where they are going. Now, if you take the directions of all these fish and then add them together, if they are all polarized, it would mean that this value will be large. When they're all moving in all directions, this value will be small. So that's the meaning of this parameter. So if you really notice what we are doing, from looking at just individuals as how they are going, we are moving away from that and trying to look at the group as a whole in this case. We are saying, okay, here is a group level parameter, or in physics, these are typically called order parameters. So it's group level order parameter that characterizes the group behavior. So here's an example, which is polarization. All right. So I don't want this to be a two-way exchange, but I want you to do this thought experiment. You remember the milling patterns that we saw where things went around? I just want to give you a 30 seconds or so to think of a metric that could possibly capture that. Okay, you can start thinking. I'm going to show that when I click next, the next one will come, which is the milling order parameter. But before that, I want you to do a thought experiment. I want to see whether you're able to think about it before I flash it here on the screen. So you guys are right. The cross product, does the job, and you have to just find the centroid and the distance from the centroid, about the centroid of the group, and you're doing. So essentially, very good. So the cross product captures this effect. And the fact that you're summing them up in both of these order parameters is basically allowing you to see whether they're all doing the same thing. And that allows you to find out whether there's consensus in what they're doing. Good, very nice. What about cohesion? So they're all together, right? What could you do? So there are many things you can do. That's a much easier measure to do. One of the things that that we've tried before, I've just wrote that down. Nothing extremely sacrosanct about it. Is that, let's say, when two agents are less than a certain epsilon distance, they belong to the same group. Because you have to specify what this epsilon is. But once you have a reasonable epsilon, you will be able to quantify whether they are of the same group or not. All right. So all of these parameters, one common thing that they do is they decouple you from the microscopic details and take you to, in some sense, the global properties or the group level properties of the system. All right. Very nice. So let's look at how one of these parameters looks for this particular data. So before that, very shortly, so this is something I mentioned earlier. So let's say you have the polarization order parameter. When all of these guys are going in all directions, they add up to 0. When they're all aligned together, they add up to 1. So that's how this captures this case very well. But I have a question for you. Do you think there are cases where this particular parameter will not capture polarization of the system the way we expect? We are assuming that all the guys are cohesive. That's why when we have things going in all directions, they can cancel out. But let's say you have half of them well polarized and the other half, and they are meeting together. For this system, M will take a value close to 0. So we are assuming that cohesion is there and that they are not broken into halves. So when you're broken into halves, you have to treat the fact that they're broken into halves. Perhaps you have to do this addition, the summing over for each individual groups and then sum it together if you still want a global order parameter. All right, very nice. So when you calculate this for data, in this particular experiment, this is what you get for 15 fish, a group of 15 fish. So the video that you saw was 60. This is for 15. Okay, but the essential aspects of the data are pretty similar, so we don't have to worry about that. So the question now is, how do you start analyzing this data? So this is for n equals 15, and this is a short time window for which this is shown. Now, what do you do to analyze this data, right? So what you're seeing here on the left-hand side are frequency distributions of this data. I hope you understand what's going on there. So M is actually a vector order parameter. What is plotted here is the modulus of that vector order parameter. Now, this modulus would vary from 0 to 1. But the vector order parameter itself will have mx and my and the frequency of getting an mx and an my. So do you understand what's going on here? So when you have a time series and it's stochastic and it's varying, one way of quantifying what's going on in the system is to look at this these frequency plots, where all I'm doing is, okay, let's say I will take a small region here. And the center, let's say, is 0.9. So I'll ask, how many times did 0.9 happen? Divided by total number of points. Even here, actually, there's no total number of points. I mean, it's just the frequency. So that comes here. And I do this for every bin. And hence, I get this distribution. Now, I can do the same calculation for the vector order parameter, which will have mx and my. What did I do to get m? Is basically I took mx square plus my square and took the square root. Now, if I, instead of doing that, if I took mx and my and looked at the combination of them and asked what is the frequency, you get this plot. All right. So these are all analyzing the data that you have. So you already moved from individual elements to a group. Now, in that group, you got a time series. You're looking at some aspect of the time series. So this is some measure. So from here, what can you conclude? You can conclude that most often fish were close to m equals 1. The mode of the distribution is at m equal to 1. You can see that is also reflected in this radius where m equal to 1, right? So what is special about that? It means that the group is polarized more often than it is not polarized. All right, so that's a conclusion that you can bring. It's an important thing to remember. All right, okay. So let's so in principle, any model that you discover should capture these elements. Whatever you're seeing as time series and its properties, the steady state stationary distribution, it should be able to capture or explain it. Now, this is just one of the features that I've talked about, which is polarization. You could measure the milling, you could measure the cohesion, you could measure near neighbor distances, you could measure the perimeter, you can measure 100 things. If a model is closer to the truth, it will explain most of these parameters, right? So there is no way we are deriving this from the ground up because there are no first principles in that conventional sense, but we are doing the opposite direction. So we're going from the data to what model we are going to explain the system. So if it has to explain all possible order parameters. Okay. All right. So really what we want to do is we want to identify a model, and we really hope that that model is right. I mean, I put right under quotes because, how do you even find out what right is without first principles basis? But nevertheless, you want to be as sure as possible that that model is representative of some aspects of reality. Okay, so how do you go about doing this? So let's take the polarization dynamics, for example. So you ask, how are the fish aligning with each other to result in the kind of time series that you saw with a particular frequency distribution. All right. So typically when you ask inverse problems, one of the most common things that you'll always spot is what is called an optimization problem. Because you're trying to ask, how do I get a model that is closest to reality or closest to the data that I have collected, right? So you can pose that as what is called an optimization problem, and this is a typical form. For those not in engineering and physics, this might look a little scary, but let me break this down for you, right? Okay. So what you're seeing, yeah. So what you're seeing here is basically we want to ask the question that I just posed in English in a mathematical formula. So how close is uh, my predictions to the reality? So the these are in some sense my predictions. What is M? M is the order parameter. So you have a model, right? You're trying to find what this model is. How do you characterize the model? We saw yesterday how the model was, right? Typically, what do you need to say? You need to tell what is the radius in which it's interacting, or if it's a topological neighborhood, you have to say how many neighbors it's interacting with. Then you may want to specify the rates of interaction. You might want to specify strength of interaction, the network topology, all of this. Once you specify all of this, you are able to run a model, a forward simulation, and then you are able to predict or able to produce some behavior which is quantified by this mi. This mi now, mi cap, which is the prediction, should be close to the observed data. If I am only using polarization, then this mi will be of polarization. But if I'm using polarization, cohesion, and a bunch of things, they can all be ordered in this fashion. It's the sum of all of those things, right? Now, what you're saying is this has to be close to that, which means I have to minimize the deviation between mi and mi predicted. And I have to find out what these parameters are that minimizes them. That is all you're conveying by writing, mathematically, this optimization problem. And then many a times that there are constraints. The constraints may be bound on what R can be, because you don't want, at the end of the day, you're posing it as a mathematics problem, and it does not care about the physical nature of the problem, right? So you're trying to bring in as much of the physical nature of the problem into the play by having constraints. What are the bounds in the rates? Because let's say a very high rate will explain the data. A very high rate may not be cognitively possible by an organism. So you'll have to have the domain tell you what these constraints are, and you bring that in. In fact, you'll realize to do better modeling, sometimes some kind of constraints will be useful, which I'll talk about in the coming slides in a particular context. But constraints essentially ground you to reality. They try to help you to reality. Of course, and this is trying to tell you how close to data you are. All right. So typically, any kind of an inverse problem that you're talking about has an optimization structure. So you can think about it in an optimization format. Some problems may be so hard that you may not be able to solve even the optimization problem that you're posing. Some problems you may have to come up with interesting ways of solving them, and you may get some approximate solutions and so on. So we are not talking about the ability to solve these problems, but typically any inverse problem is posed as an optimization problem. All right. So when there's an optimization problem, what does that mean? So just to give you a feel for it, so let's say I show you something in 1D. Okay, so let's say this is one of the parameters R. So let's say in my optimization problem, there's only one parameter R. And this is the objective function here that I'm plotting, your M minus EM cap. So let's say it has a certain structure like this. And my initial guess of R is here, which is here. Now, if I asked you, I'm solving a minimization problem where I want to minimize the deviation between m and n cap. Where is the solution? Towards its right, right? So this is the optimum solution. So what is the direction in which I have to go? Here, in this direction. So I have to, if this is my guess solution, I have to move this r towards here, which is the r optimum, which explains this data well. All right. So now the question is, if I'm here, which direction do I take? It takes the opposite direction. So how do you think about this in a more generic context? So you look at the gradient. So for example, if R old is your previous one, where should you go so that your R new becomes better, more closer to optimum? So it is always in the direction of, let's say this is the objective, this is dr. Does that make sense? What is the objective by dr? It is the slope here. And you add the negative slope. Oh, no, sorry. It should be like this. Did I get that right? Yeah. You always add the negative slope. So this adds up and you end up going in the positive direction. And when you are here, the slope becomes negative. Correct. So yeah, it's a positive. Sorry. So this entire term becomes negative. Negative of a negative is positive. So you end up moving from here to here when you're here. And at the same time, when you're here, the slope is positive, and then negative of a positive becomes negative. So you end up moving in the opposite direction. So this is what is called a gradient descent. Algorithm, which is something you should know. It's an important thing to know because a lot of optimization techniques, including machine learning and so on, use these gradient descent algorithms to optimize and find out parameters. So there are two kinds of problems now, right? So there's one dynamics problem. There's a dynamics problem where you're interested in emergence, you're interested in collective dynamics, all of that. But you don't know the parameters to use, you don't know the models to use. So you're solving another problem to find that. So this, all that we are drawing here is for the other problem, for the optimization problem that you solve. All right. So many a times it is difficult to write these problems out because of some complexity. I don't want to go into this. So you end up going for some other methods of solution which does not depend on these gradients that we talked about earlier. So one example is what is called the genetic algorithm. Just to give a quick idea of what that is. So at any instant of time, the n individuals that are written here in this cartoon that I borrowed from random source is not the n particles in your simulation. It's not the n fish that are going in your tank. This is basically, let's say so you have many parameters that you can fix, right? You have R, you have K, you have the type of interaction, the type of topology, and so on. I randomly make some 100 combinations of these. Okay, within a pool, I take 100 combinations of this. For example, one could be R equal to 1, K equal to 5. Topology could be nearest two neighbors, the top, and some other things. And another combination could be R equal to 3, K equal to 1, and topology equal to near all neighbors in the neighborhood, and so on. So I can have various combinations. I don't know which one is the right one. That in fact, that is the question, right? So if you find the right one will what? It will minimize the difference between the prediction and the data. But the question is, how do you find the right one? So genetic algorithm gives you a way to find the right one. First, it will start with, let's say, 100 of these combinations. For each one, it will do a forward simulation, evaluate how well it predicts, and then do a bunch of things, which is inspired from theory of evolution, where you have mutation, crossover, mating, adaptation, and so on. So basically, for example, mutation would be, let's say I take this particular thing. Let's say it's doing well. I want to mutate something. I would choose one of its variables and change it. Crossover would be, I take two of these guys which are doing really well, take half of it, give it here, take half of it, give it here, and create a new one. So just like how mating results in new individuals, I make new combinations of parameters from old combinations that did well. The ones that really were good, I hold them constant without changing them. So what will happen is, I started off with this 100 guys, right? The next generation, another set of 100 guys are made. And on an average, these 100 guys have better fitness than the previous 100 guys, which means they are better predicting the observed dynamics that you see. So on the whole, this is moving towards better and better solution. And the hope is that it will be able to go towards the truth, where we ultimately find the right set of combination of these parameters that will explain the data. So let me just show how that is in a simple sense. So we spoke about the forward simulation, right? So that is what you do here. The agent-based model is there. Once you feed in all the parameters, you'll be able to do a forward simulation. And then you check the objective function, your m minus m cap, to see whether the collective behaved as desired. If it doesn't, if it does, then you've already identified the parameters. But most likely it won't, because you end up starting with a guess solution, right? So what you do, you have to update it. So the genetic algorithm gave a method of updation. You could go to various ways in which you update. The steepest descent was one way of updating, and so on. And then, so basically this block is what is called an optimization framework. So you update, you do the simulation, you check again, and then update, do the simulation, check again, till you get what you set out for, the model that predicts your behavior as desired. So it really matters. So to do these things right, it really matters what you use here. What are the different parameters you use, what order parameters you consider, and so on. And another way of looking at the same thing would be, so let's say for an engineering application, just to take a quick detour. So in the case of trying to understand behavior, you have an experiment, you have the animals behave in a certain way, you're trying to understand how they behave. But in an engineering application, let's say where you're designing a swarm of robots to behave in a certain manner, you only have an idea of what they should do. So when you have such an idea, the data gets replaced by what robots should do. So essentially what I'm saying is, this way of optimization, way of thinking is very generic. Once you either have data or you have a desired objective that has to be fulfilled, you can pose that as an optimization problem and allow the optimizer to figure out how things should interact to give rise to the collective behavior, which either you expect to see or which you have observed in an experiment. All right. Okay. So coming back, I don't want to show you how to do this genetic algorithm in this particular thing. I just wanted to give you a basic framework, but I wanted to tell you how you interpret results in a generic sense. So when we did this, where we asked the question, what are the model parameters, the kind of interaction model and so on that gives rise to this kind of a behavior that is observed in data. We found out the genetic algorithm actually showed us that fish interact with just one other fish at a time. All right. So what does this mean? So we asked the question again, right? So genetic algorithm is given some answer. Is that something we should trust? So what you do in cases like this is you go to aspects of data that you have not used. So what aspect of data have we used? This frequency distribution is what I used in the problem. So now I look at other things. I look at some jump moments of the time series. I look at the effect of system size. I look at autocorrelation of the time series and so on. So look at a variety of different things which I have not used in the optimization problem. And I ask the question, does my model also predict what I see, which I have not used. And we actually saw that it predicted quite well many other things like the effect of system size and the jump moments and so on. So there was high confidence that we could place on this model, because not only did it explain the data you gave it well, but even the data you didn't use, it was able to recreate. All right. So that is how you go about in trying to answer whether the model that you have predicted or estimated can be trusted or not. But okay, now what does this mean in the context of behavior? So remember the cousin model that we talked about yesterday, and the idea or notions from big check model that were used in it, where an agent interacts with every agent in its zone. So big check, there was one zone around it. Cousin had non-overlapping zones, but all agents within that zone it would interact. But here we actually find a topological interaction, and then we also find that it will interact with only one, which is a very small number, very weak kind of an interaction. So it's a very interesting contrast to conventional models that are there. But have we answered the question in all its detail? The answer is no. For example, here in this entire view of things, I've not considered cohesion. Do my models result in cohesion, or is it independent of cohesion? How do I build that into the solution methodology and so on? So there are a lot of unanswered questions, but there are a lot of reason to believe some of these things are true and so on. The reason why I'm putting this here for discussion is the fact that when you're doing an inverse problem, your predictions are as good, or your inferences are as good as the data that you use. So I've used only things pertaining to polarization. So I've left out cohesion completely, or I've treated cohesion as an independent thing from polarization. But is that true? We don't know. So only when you solve a more complex problem where both are considered, you'll be able to answer that clearly. In the previous thing, I talked about an optimization problem and how you can pose it. And I didn't explain it in too much detail, but I hope I'm giving you a broad overview of how you think about inverse problems. So you have some data, you have predictions, you're trying to minimize the difference between the two. That's the ultimate aim behind this thing, right? So now, coming back, what did we have? We have a time series of this sort, right? You can ask a different type of question now. Can we explain the dynamics that we observe by discovering an equation that is likely to produce behavior like what you see here? So if I were to ask you what kind of an equation would produce such a time series, what would you say? It has to be stochastic. You see a lot of noisiness in the time series, the large fluctuations between 0 and 1. So this equation should be able to predict these large fluctuations. It seems to also linger around 1 for some time before switching. That also makes sense, right? We had high mode. The mode of the distribution was close to 1, which means it did linger near 1 for a considerable period of time, and so on. So you can mark all of these different details here and ask, so what kind of an equation would you expect? And then what we realize is it has to be a stochastic differential equation. So this is one way of writing a stochastic differential equation, where for those who are familiar with ODEs, this part is the ODE part. If this was not considered, it would have been an ODE, an ordinary differential equation. This is a stochastic differential equation because it has this eta of t, which is a white noise or a Wiener process, however you want to think about it. All right. So basically, what you want to understand or get is an equation where this is some term. It could be m, it could be m square minus m cube, or cos m into e power minus m, or whatever. It could be anything. But you essentially want to identify the functional forms. You want to understand the functional forms of f and g. All right. So this is an SDE. This is f of m. This is g of m times eta. So which means the noise is also scaled according to the state of the system. M is this order parameter that you're talking about. All right. So you're looking for an equation of this kind. So how do you discover this equation? So before we get into looking at stochastic equations, I think it's worthwhile thinking about it first in the deterministic case, and then we'll slowly get into stochastic. All right. Okay, so I'm going to talk about these aspects of regression and so on. So let's see what it means. So let's take an example. So here is a time series, an arbitrary time series that I have cooked up. Okay. So I'm sure you can see that there's some fluctuations, that it's mirroring some function that you already know, right? It's not some really weird structure. It's a structure that you would expect to have a certain thing. Now, let's say there are a bunch of candidate functions. Okay, so this is, I'm calling the y-axis is f, so it's f of t, or x-axis is t, and these are all changing. So now what is this, what can produce this is the question that we are asking. Now there could be a huge number of candidate functions that you can come up with. And let's say if I plotted those candidate functions on top of them, you will immediately realize that one seems to match it quite well, but the others are way off charts. Of course, I have not tuned the coefficients to these functions. I've plotted f equals t. I have not plotted f equals alpha t or something. So you really don't know what those coefficients are. But on the whole, this is how it goes. And then let's say I bring in a new set of functions. You will realize even that has a certain thing. So basically, I'm sure you already saw it. So sine t is what I have taken. I've added a bunch of noise for the data. And you see that if I take sine t by 2 or sine 2t, they won't match as well as sine t. Similarly, if I took any other candidate function, t or t square or t cube or e power t and so on, it won't match with the data as much as sine t. That is pretty straightforward, right? Pretty basic stuff. Okay. So, how do you pose an identification problem? So here is one way. Okay, so let's sink in. I've taken every candidate function and I've lined this up. So let's try to understand this well. So you have this time series, right? You have the data. And bringing the data here again for convenience sake. So every point here corresponds to one entry here. Does that make sense? So let's say there are total of let's say 1,000 entries, which means the size of this will be 1,000. What is this? 1,000 comma cross 1. So that's why I've put it as t cross 1. Does that make sense? So I'm putting every one of these quantities, the y-axis values, in this column. Now, all the candidate functions that you had, I am evaluating. So t would mean I take the t value and put it as such here. T square would mean I take the t value, square it and put it here. T cube, e power t and so on. So sine t, I would take the t value 2, sine of 2 and then put it here. So I evaluate the candidate functions here. These are coefficients that I don't know. All right. So let's try to understand this problem. So what have we posed here? So I am asking the question: when you have a matrix multiplied by like this, it means that I'm asking. So another way of writing this would be psi 1 times this column for t plus psi 2 times column for t square psi some k times column for cos 2t and so on. So I'm asking the question, what linear combination of these columns will explain the data that we observe? Is that clear? So this is what gives you the linear regression problem, where f is this is the candidate, this is the psi. And I hope you understand this comes from data. It's given to you. Once you decide on what all functions should be candidate functions, you can evaluate this matrix. So that is also known. What you don't know is this. This is the unknown. So the whole idea is to find what this is. So for our data, which is something I've already told you, it's a sin t, right? What should this be? This has to be 0, 0, 0, 0, 0, except this corresponding to this column where somewhere here, which has to be 1 and then 0 everywhere. So that's the solution you're looking for. Does that build a picture? So your equation identification problem becomes a simple linear regression problem. All right. Okay. So how do you solve a regression problem? So again, going back to the minimization that we talked about, the optimization. So you're minimizing this. So remember, I wrote m minus m cap square. Another way of writing that in vector terms is m minus m cap transpose m minus m cap, which is what I've written here in terms of f. All right. So it's the same objective function. But now, so there's something better. What is an estimate for f cap? In the previous thing, you had to solve an agent-based model, do the forward simulation, and estimate f or m. Here, we've already converted into a linear regression problem. So f cap is given by theta times that. All right. So we put that in, which gives rise to this step. Now what I can do is I can call, for simplicity's sake, I'm going to call this S. Okay. And then I can say, if I'm searching for a minima, what are the conditions on S? This is from calculus. The first derivative of S with respect to this variable, which we are trying to understand, should be 0. And the second derivative should be positive. So we are going to evaluate this for this thing. So even if you don't follow the entire thing, what you need to know is we are solving, what I'm basically showing is a linear regression problem, which ultimately boils down to a very simple formula. But the origins of all of this goes back to an optimization problem, which is like the cornerstone for many of these different inverse problems. So when I write ds by d zeta and put it equal to 0, I get this. This is just multiplying term by term of these terms. And then you start differentiating this. This will go to 0. This will vanish. One of them will vanish. And then the 2's will get cancelled out. And then when you take it to the other side, you ultimately get this. So this is a very simple formula, which in a lines code, many different, any, be it mathematics, MATLAB, Python, they will all in a single line solve this for you. But essentially, this is why it is being solved, and this is what's behind it. Where theta is something you know, so theta transpose you can take, theta you can take, then the inverse, and f is also something you know. So with all the things that you know, if you solve this problem, you get an estimate for the zeta, which is of interest to you. Now you can also take the second derivative of this term to check whether that's positive, and it's easy to show that it's positive. So you can take a look at it later. All right. So this is what is called the least squares solution or the regression problem. All right. So let's try doing this, no? So I'm going to MATLAB here. Okay. So this is unnecessary. Okay. The time t and f. Okay. So let's run this one at a time. So this is the data that I have. So the x-axis is t, y-axis is f of t. Right? If I have such a data, I'm trying to find out whether in a rigorous manner I can derive the functional form that is resulting in this particular structure. Now what do? I assemble the candidate functions matrix. So this is just a way in which I've assembled it. So polynomials, I have assembled from 0 to 4, then sine and cos functions, then j. So a huge functions list I have done. So what are those functions? These are the functions. Are you able to see this? T to the power 0, t to the power 1, up to 4, sine 0.25t up to sine 2t, and similarly for cos. So these are all the different functions which I've assembled. So you remember the big matrix, right? Where every column says there's one column for t to the power 0. There's one column for t to the power 1 up to cos 2t. There are each columns for each one of these things. Because now I have said these are the functions. So they are there. Now what do? I do regression. So there's not sparse regression, normal regression. So let's do regression. And you get an excellent fit. But I want you to take a look at what you've got here. Okay, so let's keep this on the side. So this is an excellent fit given by regression. But look at this. What was the solution we were looking for? Sine t. Right? That was the solution. But everything has popped up. So when you do a normal regression, it does not care about what you are looking for. It just gives you the best fit solution given the data. And that is a solution like this. All right. So this is not what you're looking for. So let's go back. So it looks like when you do a regression, you're unable to discover the equation. You're able to discover a equation, but not the equation that you're looking for. In this case, I know what the initial, the data where it came from, I knew. So think of it this way. For a data set that you know everything about, if you're unable to discover the equations, right, then you can't trust the method to inform you equations for an unknown system like a fish, group of fish, right? So first things first, make sure that synthetic data sets, it work well. Right now, the regression doesn't seem to work. So what do you do? So then try to characterize the solution that you're expecting. What is the solution that you're expecting? Another look at this very clearly. Only this should work. Only this should work. Both correspond to sine. Everything else should not work. So basically, only this should be picked. Everything else should be 0, which means only the relevant chi's or zetas should be non-zero. Every other zeta should be 0. Okay, that's the solution I'm looking for, and that is what is called a sparse solution. Basically, everything else is 0. Only what is required is non-zero. So it's called a sparse solution. So essentially, that's because you're looking for the right combination of functions, right? So how do you get a sparse solution? So this is again coming back to the minimization problem that we are solving. This is the problem we solved for the linear regression, and that didn't work. So what do? You bring in some element that will hopefully sparsify. Okay, and that is where we bring in a constraint, and this is the constraint that we bring. So let's try to understand what this means. Mathematically, what am I showing here? This is some kind of a threshold. It is a parameter you can vary. Do you understand what this is? So chi or zeta, okay, I keep changing. So let's just call it zeta. Zeta is the coefficient of each coefficient. If it takes a value, non-zero value, it would mean that that function is important, right? What this is doing is it's taking the absolute value of chi and adding it up. So let's say if this parameter, if there was a 2 norm, it would mean 1 square plus 2 square and so on. If it is a 1 norm, it would mean you're taking the absolute value of chi1 plus absolute value of chi2 and so on. So that is what it means. You're adding the absolute values of them. And you're saying your absolute values, overall sum of them should not exceed a certain value. You're bringing in a constraint. So it's like saying Find whatever solution you want to find, but at the end of the day, if I add all the coefficients together, it should not cross this threshold t. So this is called a one norm regularizer, and there are and the paper in which it was introduced for the first time, it's called LASSO, which stands for least absolute shrinkage. So this absolute value, you're trying to shrink them to select certain of these columns. Okay, so that's what it means. Another way of writing it, if you ever were to look at this literature further, you will also see that sometimes it comes like in the objective function directly. This can be taken here also. That's another way of posing the same problem. All right. Now the question is, does this work? Or in other words, it works. We're going to ask, how does it work? Right? So let's build this picture. Okay, let's take the case where which we can visualize. So let's take the case where there are only two of these zetas. There is only zeta 1 and zeta 2. Actually, there are many zetas, as many number as your candidate functions. But let's for now assume there are only two values of zeta 1, zeta 2. What will this look like in such a case? It will look like this. This is zeta 1, zeta 2. This will be your constraint. Does this make sense? This is an inequality constraint. It's saying the addition of both should be less than t. Imagine if this were 2 less than equal to t, what would it look like? It would look like a circle. But when it's one norm, it looked like a tilted square. If this were to be zeta, let's say fractional things, this would bend in even more. Of this. Now let's move on to a demonstration to see how that reflects. I'm going to use Mathematica to show you how to visualize this. Okay. I hope you're able to see this. So this is t. I've coded t as this thing. So now if I increase t, what does that mean? It means I am relaxing the constraint. If I decrease t, I'm making the constraint even harder. So what does that mean? So our solution should be, so what did we learn? What did we post? We said that this sum of all the coefficients should be less than equal to t, which means my solution should lie within this box. Now if t is large, which means I'm very less on my sparsification. But when my t is very small, I'm saying solution has to be here. So now what you're seeing, the next one is this is the solution. Right at the middle of the circle is the actual solution. But is that solution valid? It is not valid because I have to find a solution that necessarily is within this because that's a constraint. So what do? I keep moving out till I hit the constraint space. And look at where it hits. It hits it at an edge. What does an edge mean? It hits it at an edge which is at an axis. What does that mean? It means that one of the chi's is 0. One of the zetas is 0 coefficients. Only one other coefficient will take a value. So this coefficient is 0. Only this will take a value. So this is the reason why a sparse regression works. So when you bring in a constraint like this, it'll necessarily select a solution within the space, and the solutions most likely end up being in these axes, which forces some of the coefficients to become 0. Now let's see, if I increased t, what would it be? So this will be the solution. So if t was large enough, then the solution won't be sparse. The solution has both this, some part of zeta 1 and some part of zeta 2. But if t is much more stronger, then it's highly likely that it will always cut at an edge. So you can go back to, I'm going to give you the slides. You can go back to looking at this more deeply. But the point I want you to see is the minute you bring in this one norm regularizer into your optimization problem, it makes sure that you always get a sparse solution. All right. There are other ways to get sparse solutions. There's something called sequentially thresholded least squares, which is also very commonly used. So here it's much more simpler to understand. So you solve the normal regression problem, which didn't give you a, um, these sparse solution, but drop all terms that are less than a threshold, and then now redo the problem till you no longer have to drop terms. So that also gives rise to sparse solutions, which work quite well. So all these different things can be done. So let's try doing that now. Okay, let's go back to our MATLAB demo. So same, this is not required. Okay, it's the same thing. Run it, the same data. I assemble the candidate function. So let's look at the candidate functions. Okay, it didn't run. Yeah, so these are the candidate functions. Now, I do a sparse regression. I'm going to use the first technique that we talked about, the lasso. I'm going to give a lambda value. So let's begin with a very small lambda value. So here lambda is the opposite of the t that we talked about. When lambda is very small, close to 0, it becomes the least squares problem. It is like 1 by t. It has a 1 by t connection. So when I keep increasing lambda, what will happen is the t will keep reducing, the t that we had in the... Okay. So now let me run this thing. You start to see that many are 0, but many also have values. So let's look at prediction. So the black dotted thing is the least squares prediction. The orange line is the prediction from your prediction from the sparse regression. So now let's run this again with a different lambda value. Let's keep reducing. So what do you get? Again, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 of the terms have become unimportant. Reduce it even more. Now you have many more going on. Now only 1, 2, 3, 4, 5, 6 terms are only popping up. Right? I increased even more. The prediction is quite good. Look at which term has popped out. The one corresponding to sin t. So it's very interesting, right? So the minute you add a regularizer to your optimization problem, it starts to now heavily throw out terms that are not important because of the geometrical representation I showed you. And hence what happens, slowly as you tune this parameter lambda, you're able to remove one term at a time and come to a point where you can actually get the term that you're looking for. Now, what is this lambda that you have to choose is still up to you. There is no principled way to actually figure out. Perhaps there are other things like cross-validation and many other things that people use in machine learning now, which could be used to automate this. But still, this is a parameter for the optimization itself. So if you look at least squares optimization or the first linear regression, there was no free parameters. You had theta, you had f, you do that formula, you get least squares, straightforward. But now in the sparse regression, you have a parameter that you have to tune, which means you have to tune it with some care that you take. All right. So let's go back. What have we done so far? We've have some data, some time series, f as a function of time. So we just tried to fit some function to it. And in that context, I showed you what it means to fit, a functional form. But essentially, what did we want? We started out trying to understand whether we can derive functional forms for differential equations and stochastic differential equations. So this is an ordinary differential equation. Let's say there's a true model that produces some data. What will it produce? You'll have timestamps, and at those timestamps, you will have the corresponding value of x. That is what this model will produce, right? Now, from that, what can you estimate? You can estimate the derivatives. So let's say you have x1, x2 at time t equal to 1, 2, and so on. All you have to do is x1 minus x2 divided by delta t. So this is 1 delta t, 2 delta t, and so on. So by doing this or any other sophisticated smoothing and filtering and so on, you can essentially get an estimate for the derivatives. And once you have that, you can pose the same sparse regression problem, where now your left hand side is all this estimated dx by dt. These are all your candidate functions evaluated using t and x, and these are the things that you need to find out. All right. Um, this is what was so you can use sparse regression to identify this, and this is and then once you do the sparse regression, identify a candidate set of functions for f of x, you have to necessarily carry out a forward simulation to see if it predicts. Okay. Now, so what is this? So this was initially published and became very famous by this group called Brunton and his group, Steve Brunton from New York University. This was featured in PNAS. So where they showed a Lorentz system. For those of you who don't know what a Lorentz system is a prototypical example for a chaotic system. If you see, this looks like a butterfly, right? So you would have heard the term the butterfly effect. So this is a chaotic system, which means that the changes are kind of unpredictable, quote unquote. And so basically, when you solve these system of equations, it gives rise to this behavior. Now they showed that you can pose this inverse problem where x dot, y dot, and z dot are evaluated from data. There are these candidate functions, which are again evaluated from data. And then there are these coefficients, which you have to find. And they showed that when you solve it, you can find it. And they call this package that they developed or this method as SINDI, the sparse identification of the nonlinear dynamics. So they have an associated package called PySINDI, which does that. So let's take a quick look at the demo. All right. So what I've done is a Colab notebook so that, when I send you the slides, you have access to this notebook. So this was, and it installs this PySINDI, which is a package that these guys have developed and have made available. So I'm connecting. So for those of you, I'm assuming everyone knows Colab. Colab is like you're connecting to a Python environment in some computer somewhere. So anyone can do this. You don't have to install anything on your computer when you're trying out all of this. So I'm installing in that computer that I've connected this package PySINDI. Yeah, 4 seconds install. And I'm going to redo what these guys have shown to us. Okay, these are the Lorentz equations, the same thing. So let's solve the Lorentz equation. So there's an ODE integrator that solves this Lorentz system of equations. And this is the data that looks. You see, quite very different. You'll see that when you plot them, all these three together, it will look like that butterfly. But now this is plotted as a time series. Now the aim here is to find out what differential equations gave rise to this. So each one of these curves, what is the differential equation that gave rise to it? So we are using the same PySINDI thing, and it is going to run the optimizer, and then it shows its predictions. X dot is 9 minus close to 10 minus 10x plus 10y, and so on. So if you go back, you realize these are the sigma into y minus x. So 10 minus 10x and plus 10y. Then what is rho? There's a 28 minus z times x minus y. So let's see, 28, almost 28x minus almost, this is not x, this is into sign. This is my, xz. Yeah, correct. XZ, X, and minus almost 1 times Y and zero point 0.1 times something else. So you see that it is able to predict the equations to considerable degree. All right. So let's look at another example. Oh, okay. Before that, the forward simulations. So you simulate now the and show the original and the estimated. You'll see that they look almost identical. In fact, I asked my student, why don't you put them on top of each other? He said, you won't be able to differentiate the two. So it very nicely captures the equation. Close as good as the data is, the estimate is, and so on. All right. So this is the example that works well. So that brought that paper a lot of interest. So here is another model of interest to ecology people. There's a Lotka-Volterra model, the famous predator-prey model. So let's solve this. Wow, it's quite fast. Okay, this is how it looks, predator-prey. There are oscillations out of phase of the predator and prey. Now let's try to see whether we can extract the equations. And voila, it does. So this is 2.5x, 4 minus 4y. This is 2.5x and 4y, 2.5 and 4. Okay, 2.5, 4. Then 0.5, 1.5. 0.5 minus 0.5, 1.5. You see that it's able to pretty well, predict these equations. So let's do the same thing. Let's try plotting them. And you see that the predictions are spot on. So given enough data, and data in a certain format and so on, it is able to predict the equations back. All right. So what we have also done is there are problems down here where we've set up the Cindy. This is for you to run. None of them will give you the answer you're looking for. The reason being, I want to basically make the point that this is not some kind of a magic box where you throw data, you'll get an answer. You throw data, you have to make sure many things are right. You have to make sure the number of data points you've given is right. Then whether you've spanned the entire phase space. For example, from the one side, it will look like, my God, how did they, take a chaotic equation and get it back? It's so hard to think of chaos, right? I mean, you may think along those angles, but if you really think about it, in a chaotic system, X, Y, Z vary across the phase space and nicely go everywhere. But that is not true for all differential equation systems. So let's say if your system has not spanned the entire phase space, then and you throw that data into PyCindy, it's likely to give you answers that don't match. If you have not have enough, accuracy in your estimates of derivatives, it is likely to fail and so on. So there are many reasons why it could fail. So we have set up the problem in such a way that you won't get answers. So that is the last part of this tutorial, PyCindy tutorial. We would like you to work on it and see if you are able to just do the right things to get things to work. All right, so let's go back. Okay, so essentially we are moving towards stochastic equations, right? That's where we started off. Then we said, okay, let's look at deterministic cases. Then we looked at just the time series. Then we came back to ODEs, and now we're coming back towards on our route towards SDE. So essentially, we want this equation where it's not just f of m, which is what the Cindy did, but also g of m. So how do you go about doing this? So there's a lot of theory for SDEs. I'm not going to get into those theoretical details here, but we know from literature what ways in which you can derive f and m. Okay, f is what is generally referred to as the drift, and g is what is referred to as the diffusion. The formula for f is something like this. On an average, at a particular value of m, what is the change that you expect? So it's like it's very similar to the first order, derivative of an ODE that you expect. Diffusion, on the other hand, is about this change. What is some of the variation that you see? All right. I don't expect you to understand this immediately. I'm just giving you a feel for it. So remember what your equations were. It was dm by dt is equal to some f of m plus g of m eta, right? So this is just the ODE part. This is the SD, what makes it SDE. So this will have the same features as the OD. So it's on an average the rate of change of M. That is exactly what this is. This is after I remove this, from my estimate, what is the correlation that you see in some sense. So diffusion kind of, what is the spread that you see about the average is what it's quantifying. So now you have these formulas. What you'll be able to do is extract from a time series these formulas. So let's just try to look at an example. So even before we go to the fish problem, let's again redo this for an example, synthetic data that we know. Okay, so here is an SDE. So clearly, what is the F here? This is the F. What is G here? It is just a constant, right? So if you simulate this, you get a behavior like this, right? So we have developed, when I say we, it is me and my collaborators. Um, uh, when I was part of IISc, this is from the Center for Ecological Sciences, IISc, Vishu Guttal's lab. We've developed this package called PyDaddy, which is a Python package for data-driven dynamics, which does a lot of this SD extraction given data. So and it's a very well-written document, which does this along with a lot of diagnostic tools. Let's just go there and take a look at what it says. So it's quite, so I encourage you to try this at some point. Let's just do one of these. All right. So yeah, so this is it's another Colab file. You're first connecting and then installing the package there, and then import all the functions that we need. Yeah. So now I'm going to the same model that I initially showed. There are, of course, different models here that you can, try yourself. The link to that is there. So this is part of the example notebook that is part of the package, but I put the link in my, PPT as well. Okay, so let's visualize the drift and the diffusion. The actual drift is minus x, and g square is 2 because g is root 2. All right. So this is the simple ODE. SDE. Now you simulate the SDE using a SDE integrator for enough time. Yeah, done. And then you plot how that looks. So this is the time series for a selected time. And then this is the distribution. So it's mostly the mode is around 0 and it's distributed about it. Now we have to recover the diffusion. So this is the main thing that runs, which tries to recover. So this is the only thing we'll see in today's lecture, because a lot of other details here which are beyond the scope of today's lecture. So this is just a sample time series. It's autocorrelation function and some other things that you would want to see. Now here is the estimate of the drift. You see that it captures that linear. So there are some exceptions like this, but you sort of gets the linear decreasing. And the diffusion, the sort of a constant thing. Of course, there are some blowing up towards the edges, but otherwise you get this. So now you can go back and do your sparse regression to get functional forms for this F and G. And look at what you get, close to -1. And these are all very small parameters. But this is a large parameter. So here, many more parameters are estimated when the tuning is automatic. But if you tune it yourself, you get a reasonable estimate. G square estimate is 2. Does that make sense? So again, I've shown you that for a synthetic example, this works. So you are able to estimate your F and G based on your drift and diffusion formulas. And then from those formulas, you're able to do sparse regression and get functional forms for your equation. So we started out with an equation which has g of 2, g square of 2, and g of root 2, and f of -1x, and we get the same thing. There's a bunch of other things here which you can take a look at in your leisure. Okay, so now let's come back to finally what we want to do. Okay, so this is the time series I've been flashing from the beginning. So let's finally make sense of what this is and from what can we learn after we get the equation from this. What do we learn, and is it worth all this effort, right? So when you do the Cramer-Moyal coefficients, this is what you get. Of course, see, this is a vector order parameter. Remember, I've been showing you one time series. It's actually vector order parameter. So you have mx and my. So when you plot your f and g functions, so this a and b are from another era of notations, but this is basically your f and this is your g. You get these kind of functions. This is quite a linear thing, right? This has a certain non-linear shape. So when you run your sparse regression, this is what we get. You get an f, which is minus alpha m. We get values for alpha. For convenience sake, we put alpha. And g, which has this form, which has a root of 1 minus m squared. So this is the STE that you estimate. So it's interesting, right? You start with a bunch of fish moving around aimlessly. And when you do a serious analysis rigorously of its data, you end up deriving an equation of the sort that you see here. So you have dm by dt is minus alpha m and this. So now that you have an equation this simple, we should be able to make sense of the dynamics, right? So let's just soak this in. What does this tell us? Okay, first, the fact that that there is so this is the only deterministic part. All of this belongs to the noise. And this is typically called the multiplicative noise term. Now, what is m? It's how much ordered it is, right? So if an m is a large value, it means large order or close to 1. M close to 0 would mean low order. Okay. Now, let's say we consider only the deterministic case. What happens? This becomes your equation. Now, what is the solution for this equation? It is m e power minus t by alpha or something of this, or alpha t. All this tells you is that m goes to 0 with time. That is what this equation is predicting. And let's say you add some noise, throw in some noise with it, where the noise is a constant, not the kind of g that you had. Okay, what do you expect? You expect the dynamics to be about 0, right? But what do we know of our system? Where was the mode for m? Close to 1. If you remember the annulus, it was close to 1, which means there was order in the system. This is saying if you only consider the deterministic case, it tells you that there's only disorder that you expect. But this is what we see. This is like a cut of the 2D plot. You actually have to find mode away from 0, which means the structure of this is very important. So order actually emerges from the structure of the noise that you have. This is a non-intuitive result. So what does this mean? So let's just look at this, right? So when this m value is close to 0, g is the largest. When this is close to 1, g is the smallest. Can you see that? When m is 0, it's beta plus alpha by n. When m is 1, it is alpha by n. And alpha, beta are all positive numbers. Now, what does this say? When the system is close to disorder, there are huge fluctuations in m, which will push the system to order. And when it's ordered, the fluctuations are small. So then the system ends up residing in those cases for much longer time. So the upshot of all of this, even if you don't understand the details of this, what I'm trying to essentially say is you started off with data from a system of animals doing some kind of a behavior. Now you have an equation that you can interpret and try to understand, and which has come through a quantitative treatment of the data. Now that equation is now informing you the kind of nonlinear dynamics that you're observing in your system. Does that make sense? So all of this is what makes this entire process worth it, right? So you started off with some data, you get some equations, and now the equations inform you of the kind of dynamics and throws light on what's going on in the system and so on. And there are a lot of interesting connections. You can look up a paper on this, so which has a lot of details of this. Is at the level of the group, right? You can ask the question, what are the interactions at the level of the individuals that lead to this? And you'll realize only when they choose one neighbor to interact with, it will result in this equation. The minute they choose more than one and they start to average their interactions, this minus m will become m cube minus m or something of the sort. And it will result, and this itself will have a fixed point outside of 0. So, meaning to say, these are all connected, well connected. It is because fish interacted with one fish at a time, it produced a very weak effect that ultimately resulted in this. I'm not making the connections here, but I'm telling you how independently through a genetic algorithm and things of that sort, we landed in the model. And through this analysis, we landed on the equation, and they all meet at some point to making sense of what's going on. So that brings me to the end of today. So these are all details, but end of today's lecture on this. I'd be happy to take questions here.